Hi, everyone. I'm Meixu Chen, a PhD student from Geographic Data Science Lab in University of Liverpool, currently a postdoc at UCL Geography. Thanks for having us to present at this year's GISRUK conference. I'll show you some preliminary results of our ongoing research that using bike sharing data to profile the dynamic pattern in New York City. I'll unfold my presentation through 5 sections. Start with the context and motivation of our research, and introduce you how the data look like and how to pre-process it for our analysis. Then I'll show you the methods we used to profile travel patterns and some preliminary results. And finally, a brief summary and our future works. Let's get started with introduction part. So, bike sharing system is a short-term bicycle rental service for inner city transportation that provides bikes at unnoticed stations. Unlike traditional bicycle rental services, bike sharing system is usually designed as part of the urban transit system with less cost, increased flexibility, and easier access. And bike sharing has gained increasing popularity that over 2,000 systems are currently in operation over the world by 2020. It's good for public transit efficiency, public health and well-being, and social good. And previous studies have focused on statistical patterns of bike sharing trips, analyzing cyclists' travel behavior, optimizing system operation, and the relationship between multiple variables and the bike sharing ridership. But limited studies have analyzed the dynamic usage of patterns of bike sharing docking stations, which is also important in terms of urban dynamics and human mobility. Actually, this kind of study could be used to monitor travel demand, infer functional characteristics, and finally maintain a sustainable bike sharing service. So City Bike of New York City is the largest privately owned 24 hours, 7 days a week bike sharing system scheme in North America since 2013. It has about 19,000 bikes and over 1,000 stations. It was designed in a quick, convenient, and affordable way to get around the town. Since the system continues to expand, several docking stations were only built and open in the second half of 2019. So for data integrity and continuity, we only selected stations that were totally operational before 2019 in our study. What's more, most early existing docking stations located in Manhattan, so we just conduct our analysis in Manhattan. Our primary aim is to profile the dynamic pattern of bike sharing stations based on their usage using city bike data. We think the research results could help urban planners or decision makers to identify the primary usage of each docking station, further examine the current performance of bike sharing system operation, and so improve their services. Now we'll move on to the data section. We extracted trip records from CityBike's open data repository in 2019. The general data structure is presented in this table. So each row represents a finished cycling journey with origin and destination docking stations of a single user. Both spatial and temporal information are available for us, that making it possible to profile dynamic pattern of stations. This figure displays the spatial distribution of city bikes docking stations in New York City, and the aggregated inter-station origin-destination flows in Manhattan. Most flows located at the south, which is actually the downtown of Manhattan. After data cleaning, about 86%, over 17 million bike trip records left for analysis. To profile the docking stations temporal usage pattern, we use start and end. So that's outbound and inbound information to formulate a weekly travel profile for all 504 stations. The trip data was aggregated into 24-hour time bands by day of the week. So in total, 336 temporal variables. This means that each station contains 168 variables. So that's 24 hours multiply 7 days for start count, and 168 variables for end count. This figure captures two major peaks during weekdays and random spread trips during weekends. Next, I'll show you our methodology of the research. TF-IDF, so it's term frequency inverse document frequency, is the first method we used. This is one of the commonly used weighting schemes in text mining. It measures the importance of a keyword or phrase by comparing it to word frequency in a couple of documents. And TF-IDF has functioned to reduce the importance of words if they appear everywhere in the whole document. So for example, the common stop words, while increases the importance of those have a high frequency at a particular document. So for example, in this case, auto repair. So inspired by this mechanism, we implemented TF-IDF through this formula on our dataset to weight the words, sentences, and document corresponds to one temporal interval with 336 temporal intervals in a single station. Here in our context, WIG is the weight of a temporal interval in city bike docking station. TFIG means the frequency count of that temporal interval among all temporal intervals in a station. N represents the total number of city bike docking stations. So in this case, 504 stations. And DFI means the number of stations that contain the temporal interval. So higher weights will be assigned to time periods that experience high volume of cycling flows. This measurement can capture random patterns, such as patterns at weekends, which are hard to identify without TF-IDF weighting measurement. This also help improve our later clustering analysis in producing more distinctive and robust results. We weight the outbound and inbound frequency assembled in each station to get a distance metric. After that, we conducted hierarchical k-means clustering to characterize different temporal patterns. And through gap statistics methods, we assign 4 as an optimal number for the key. So based on the methodology, I'll show you our preliminary results of the research. This heat map shows 4 temporal clusters from 504 stations. So darker color means a higher probability of appearance of the temporal interval, and lighter color means lower probability. And stations grouped in cluster 1 are more likely to be laser oriented. We can see the winners high flows at both inbound and outbound usage during the non-working time. So it's 7 p.m. to 0 a.m. at weekday night and 10 a.m. to 0 at the weekend, but low appearance during working hours. And for the cluster 2, it's predominantly witness high outbound flows during the weekday morning and high inbound flows during the evening peak times. This pattern indicates a typical residential-oriented functionality. And stations classified in cluster 3 shows a reverse pattern compared to those in cluster 2, implying a typical workplace-oriented usage. And finally, cluster 4 is similar to cluster 2. So these stations might also serve as a residential-oriented usage, but they witness a relatively high flow volume at one or a few temporal intervals before the conventional peak times. So we think that it might means off-peak travel. I won't unfold all cluster results here, but I'll discuss the first 2 clusters as illustrations. So cluster 1 is viewed as laser-oriented cluster. The overall docking stations located across Manhattan, while the majority located in lower Manhattan. So that is downtown. This is the area where some of the city's most famous buildings and tourist attractions, and it implies that these stations are more likely for people random entertainment usage. And cluster 2 is identified as a residential-oriented functionality. So stations are primarily aggregated at Upper West Side and Upper East Side Manhattan, which are known as residential areas. Well, let's end with a summary and our future works. So this research applies TF-IDF weighting measurement combined with a hierarchical k-means clustering on the 2019 cycling transactions from the Citi bike sharing system operating in Manhattan of New York City. We studied the spatial temporal usage pattern of its docking stations. We classify 504 stations into 4 main clusters that feature dynamic usage, includes laser-oriented, residential-oriented, workplace-oriented, and off-peak oriented functionality. And one of our limitations is our temporal division is not systematic. Some trips may less than an hour, which may not be captured in an hourly interval. So our future work will further explain and evaluate the characteristics of these identified cluster results. by looking into the socioeconomic, geodemographic, or land use characteristics of the surrounding neighborhood, such as using POI, a point of interest data, to see the spatial context of these our temporal clusters. And besides, our method framework could be deployed in other cities if bike sharing data are available, such as London bike sharing data, as Xiaowei just introduced. Yeah, and thanks for listening. Please feel free to get in touch with Yunzhe and I for further discussion if you are interested. Thank you.
In terms of your future work, how do you see possibly using things like the geodemographic data? Do you have any thoughts on how you might actually incorporate this in?
So we try to combine geodemographic information. So we try to do another clustering, but based on the spatial information, and then do the comparison with the temporal clusters and spatial clusters to see their common characteristics. That we try to use that geodemographic information to explain why we'll get that kind of temporal clusters.
Did you use 336 intervals of a station as input data to clustering?
Yes. Yes. So here we used 336 stations, temporal intervals based on 504 stations. So we cluster based on 336, which includes outbound and inbound separately, and 168 for each.
Question in the Q&A. What was the motivation on using TF-IDF?
So we try to use TF-IDF. That's our innovative method here. So because with this method, we could try to capture some random patterns. So for example, if we didn't use TF-IDF, we have to remove the weakened data, because that pattern we can't capture. But with the TF-IDF, we can capture the most important patterns in that temporal intervals.
Can you explain some use cases for these clusters? Can we identify areas more suitable for cycling or active transport in general?
As I mentioned in our in the presentation, so possible application in the future is to combine other characteristics to see why these temporal clusters we get for the stations. So for example, if we use the point of interest data to see our spatial our temporal clusters, we can explain why. So for example, some stations we define as labor-oriented or workplace-oriented. It will be why this function will have why these stations will have these functions. So for example, for workplace-oriented, so the neighborhood POI might be some CBD or some restaurant or some office buildings. So we try to answer the questions, like that.
So the question, what is the difference between k-means and hierarchical k-means?
So if you use k-means, you have to run several times to get so like robust results. So you have to like set seed to get a robust result. But if you use hierarchical k-means, you don't have to run several or many times. You just can run once or twice to get the most robust results.